Okay, good afternoon. Welcome to this edition of the NITheCS Colloquium. It is my pleasure this evening to introduce to you Professor Florian Luca. Florian is originally from Romania, where he did his undergraduate studies, followed by a PhD in Alaska at University of Alaska in Fairbanks. After which he traveled a little bit across the continent, from the US to Germany, to the Czech Republic, Mexico, to land back in South Africa at the University of the Witwatersrand first. And then he was stolen by Stellenbosch.
Maybe.
and he moved to Stellenbosch not so long ago. He's probably the most productive mathematician that I've ever met.
Thank you.
Yeah. So, but we won't do numerology now because he will speak about number theory. That wouldn't be appropriate. Yeah. He won many awards that I won't read one after the other. But he's also a member of the Academy of Sciences of South Africa and on the African Academy of Sciences. Yeah. So, Florian, thank you very much for agreeing to give us a colloquium, and we are very much looking forward to learn about the famous problem. Yeah. Thank you very much.
Thank you very much, Francesco, for this opportunity. And thank you guys for coming to my work, to my conference. So today I will tell you something about the Skolem problem. What is it? Why is it important? And what do we know about it? So the question that we start with, from let's say a computer scientist point of view, what is the simplest class of programs for which deciding termination or halting, it's not an obvious question? And the answer is the simple linear loops. So the simplest most program you can think of. So if you've ever taken a course in computer science as an undergraduate, then you would see something like this, where you start with a system of parameters. In this case, they are denoted x, y, z. It has some initial values there. And while x is not equal to 0, then move those parameters around. Move 2x plus y to be the new x, y plus 3 minus z to be the new y, and z to be, the new z is minus 4z plus 6. And what is important, so this is, let's say, a particular case. More generally, you start with some vector, we call it A, which has some components. In this case, it's 3 components. And while the first component of that vector is not equal to 0, then change x in m times x, where m is some matrix. Well, this is not exactly like that because of that plus 6 and plus 3. So you can also add something else to it. You can say x goes to mx plus some other vector b. And this is one instance. A different instance would be to test something else. Instead of testing whether the first component should be non-zero, you might ask whether the first component is greater or equal to 0, and then do that assignment. So those problems have names. The first one is called the Skolem problem, and the second one is called the positivity problem. So you can say, what is the problem? Because you apparently might not see the problem. The problem is deciding whether a loop like this would ever stop. When will a loop stop? For example, in the first case, the loop stops when x is equal to 0. So once x is equal to 0, then it dies out. It doesn't continue. And the positivity problem, if some value x1 becomes negative, then it stops, because you're allowed to do this assignment only as long as x1 is greater or equal to 0. So this is the Skolem problem. The instance, it's a square k by k integer matrix, M. And the question, is there a positive integer n such that as I keep on multiplying the matrix, applying the matrix m to x, and then I apply it again and again and so on, the top right entry of m to the power n is 0. So this is the Skolem problem. And the positivity problem asks the same data, a k by k matrix, m. And the question, is it the case that for all positive integers n, the top entry, the top right entry of m to the power n is greater or equal to 0? And this can be formulated in the language of linearly recurrent sequence. What is a linearly recurrent sequence, or LRS? It's a sequence of numbers, for simplicity it's just integers, with the property that as you move along, you construct every term of the sequence by taking a linear combination of the previous k terms of the sequence with some fixed predetermined coefficients, a sub 1, a sub 2, up to a sub k. So this sequence is given by two k numbers because you need the first k initial values, and then you need those coefficients, a sub 1, a sub 2, a sub k. Once you know this, you know everything about the sequence. So you can construct inductively if you want the nth term. So here is an example. The example is the famous Fibonacci numbers. What are the Fibonacci numbers? It's a sequence which starts with 0 and 1, and in such a way that every term is the sum of the previous two terms. So if I add 0 plus 1, I get the next one. If I add 1 plus 1, I get the number 2. If I add 1 plus 2, I get the number 3. 2 plus 3 gets the number 5. And it keeps on going like that. And the order of a sequence, it's how long is this recurrence. So you need two terms in order to construct the next one. So the Skolem problem can also be reformulated by saying, suppose that you take such a gadget, a linear recurrent sequence. So somebody gives you these k initial values and it gives you these coefficients. And the question is there an n greater or equal to 0? Is there a term of the sequence which is equal to 0? And you have to decide that. To decide that, sometimes the word deciding is confusing. What does it mean to decide? You see, it's if there is a 0 and you compute them, eventually you will find it and you decided that there is an n which is equal to 0. But let's suppose that there is no n for which the sequence is equal to 0. You keep on computing and you never find an n such that un is equal to, but you can't go all the way to infinity. You will have to stop at some point. And you will have to say, listen, I've checked so much that since there is nothing up to here, then there can't be a 0 from here on. So this is the decision problem. It's can you, after some finitely many steps, can you conclude, okay, I haven't found anything, and because I haven't found anything, there can't be, from now on, other things which are equal to 0. And the positivity is the same instance. You're giving the linear recurrent sequence. You're only asking, is it the case that it is always greater or equal to 0? If I compute the first 10 million terms and they are all positive, can I decide, can I say, okay, there's not going to be any negative term ever? And here is what, this is what we always do in the academia. We find people which are smarter than us and we quote them. So here is one quote from Terence Tao, which says that it is faintly outrageous that this problem is still open. It is saying that we do not know how to decide the halting problem even for linear automata. And here's a quote from Richard Lipton, who's a professor of computer science at Georgia Tech. He's retired now. He calls this a mathematical embarrassment, arguably by some distance, the most prominent problem whose decidability status is currently unknown. Okay, but some things are known. Well, let's see what is known. Not everything is unknown. So let's take the set of zeros of this linearly recurrent sequence, and there's a theorem which was proven by this Skolem guy in 1934. And then it was proven in higher generalities by Mahler and by Lech in 1935 and 56 and 53. What do I mean by generality? Skolem just did it for the integers. And then these other people did it in more general. For example, algebraic numbers, which I'm not going to talk much about them, or complex numbers and so on. So what's known about this? It's known that if you take the set of all these zeros, it has a regular part, which are like arithmetic progressions, let's say all even numbers or odd numbers that give 1 if you divide them by 3, and a finite set. And here is an example of those guys. Oh, there is no example there. I can, an example of this guy is, for example, you can take the sequence which is 1, 0, 2, 0, 3, 0, 4, 0, and so on. So what it does, on the odd numbers, it behaves like all the integers, 1, 2, 3, and so on. And on the even numbers, it's constant 0. And it's easy to write some recurrence for that. It's easy to write that un plus 4, I believe, is 2un plus 2 minus un, or something like this. And you can see that it will have, let's say, all even guys are equal to 0, and those zeros are understood. And then there is another finite set. In this case, that finite set is empty. The interesting thing about it is that now you can take this sequence, and the fact that these zeros appear, it's something called a degeneracy. So what is a degeneracy? Somehow this infinitely many zeros appears because you take a constant zero sequence and you feed it into some other sequence that otherwise has nothing to do with it, like the sequence 1, 2, 3, 4, and so on. We said, let's space them out. Let's place them only on the odd integers, and on the even integers, we feed them with zeros. So you can do that with a bunch of linear recurrent sequences. You can assemble them together and you get a different one. And some of those guys might be constant zero, and those guys are understood. So if a sequence can be sort of sliced in that way, there is a very concrete mathematical terminology for that. It's called non-degenerate, but I'm not going to bore you with the details. But the important thing now is that you can reduce your study to these non-degenerate sequences. And for the non-degenerate sequences, strange enough, we don't know how to compute the zeros, but we know that there are not too many of them. That is, if somebody gives you a number k, let's say a sequence of order 10, then that sequence has at most exp to the exp to the 700 zeros. That's a very large number. And that's an improvement, because before it used to be exp of exp of exp of 3k log k. So probably the answer is, you can ask, well, what is the answer? Is it linear? Nobody knows what the exact answer is. There are examples which have quadratic number of zeros. There are linear recurrent sequences of order k that have about k squared zeros. So you can ask, what is really the champion? But certainly exp of 70k seems a bit too far-fetched. So I already mentioned that a sequence is degenerate if it can be written as a merge of lower order sequences, which can be assumed to be non-degenerate. And non-constant, non-degenerate linear recurrent sequences, they diverge in absolute value. So if the number n is sufficiently large, then the absolute value of this nth term exceeds any number you want. In particular, that's why it has finitely many zeros. The problem is that we don't really know how it goes to infinity. We can't control that. And here are some examples where this Skolem problem appears. In theoretical biology, you can imagine that you set up some model between the prey and the predator, and one of them, let's say the prey, has to always be positive, otherwise the system dies if it gets to zero. Then it's software verification, dynamical systems, weighted automata and games, control theory, quantum computing, statistical physics, formal power series combinatorics, and so on. So let's go back to that example. What do you think? Does this program halt or not? So what we can do to it, we can reduce it modulo 3. Every time you see a multiple of 3, you ignore it. So let's see if we do that. What do we get? Well, let's see. We start with 1, 0, 0, right? So the next guy, it's going to be 2 times 1 plus 0, which is 2. This is the value of the next x. The value of the next y is going to be 0 plus 3 minus 0, but we say that 3 is the same as 0 because we are looking at it mod 3. So y remains 0, and z, it's minus 4z, but z was 0. So minus 4z is minus 4 times 0 plus 6. 6 is a multiple of 3. Again, we ignore it. So this means that it started with 1, 0, 0, and modulo 3, it became 2, 0, 0. So you just doubled the first guy. But then if you go again, you double again that 2, it becomes 4, but modulo 3, it becomes 1. So this is the explanation of what you see there. So x's, it's 1, 2, 1, 2, and so on. The y's are always 0, and the z's are always 0. So what is the conclusion? The conclusion is that this program never stops because it never gets to the value 0. So you can count those things modulo a number m. So let's go back to the Fibonacci sequence. The Fibonacci sequence was introduced as a problem about pairs of rabbits mating under ideal conditions in such a way that they mate for 1 month and then they don't have an offspring, but then after 1 month they become an offspring. So it starts with the first pair. After month 1, it's still that first pair. After month 2, it becomes 2 pairs because it's the initial pair plus the pair that mated, and then the pair that has babies, and then it keeps on going like that. It fulfills that recurrence. Now this sequence, interestingly enough, it has a 0. You can say, what do you mean it has a 0? It's always positive. It's true, but let's try to play the game that we played before. We reduce it mod 2, so we pick up only the odd or even numbers from that list. So the first two are odd, they are 1, the third one is even, the fourth and the fifth are odd, the sixth one is even. So you can see a pattern. Every number that's in a location that's a multiple of 3 is even, and if the location is not a multiple of 3 is odd. Let's try to do it mod 3. If we do it mod 3, we see that that 3 which is in the fourth position becomes 0. And then if you go 4 position more, the number 21 is also a multiple of 3. That's also a 0. And you go 4 position more, 144 is also a multiple of 3. So that's 0. And in between you have 1, 1, 2. And then 5 becomes a 2, 8 becomes a 2, and 13 becomes a 1. So if you look at it mod 3, it's periodic. It has period 6. And it goes 1, 1, 2, 0, 2, 2, 1. And then it repeats 1, 0, 1, 1, 2, 0, 2, 2, 1, and so on. And the same happens with 4. It has a periodic pattern. Of course, this periodic pattern becomes more and more complicated. As you go to modulo m, it could be as long as about the square of m in the worst case. And modulo 5, for example, it's period 20. But the point is that there's always zeros appearing in here. Is there an explanation for the fact that there's always zeros appearing in there? Of course, there is an explanation. And the explanation is that, in fact, the sequence has a 0 in it. Except that you don't see it because I was mean and I started with 1, 1, 2, and so on. But you can imagine going into the past. If I go into the past and I want to put a number to the left of the first one, in such a way that the sum of that number with the first one is equal to the second one, then what number would that be? Would be the number 0. So somehow I have a sequence, it has a 0, but I chop it and I only show you the part that's after that 0 in the future. And you say, well, there's no 0 there. Sure, there's no 0 there, but there was a 0 in the past. And that 0 in the past, because of periodicity, it creates the zeros in the future modulo every number. So this is the explanation that what I said, it's a sequence that you would call reversible. That is, you can continue it to the left in such a way that if you sum up any two consecutive numbers, even on the red side, then you get the next number. So 2 plus minus 1, it's equal to 1. So if you go into the left, then you create that first 0. And then the odd positions, they remain the same, like that 1 and that 2. And the even position, they change signs. Like the minus 1 is the symmetric of the second one, but it's with a negative sign. And minus 3 is the symmetric of 3 with respect to that 0 position. And it has a negative sign, and so on. So this sequence is bi-infinite, and it's periodic modulo m for every m. So this is the classical Fibonacci sequence, which I already showed you. And then there are other ones which you might try to reverse. For example, let's try to reverse this one. If you try to reverse this one, that is fine. It's just an arithmetic progression. It's all the consecutive integers. You can even go into the past, and it's okay. Then what about this one? So every time you multiply the previous number by 2, you get powers of 2. 1, 2, 4, 8, 16. Can I go into the past? Yes, you can go into the past, except that you have to think outside the box. You go into the past, that way you're not going to obtain integers, but you're going to obtain rational numbers that have powers of 2 in the denominator. Like in order to get that 1, who do you have to multiply by 2 in order to arrive at 1 is a half. And then you keep on going into the past. So these things would be called z-reversible, and these things are called not z-reversible, meaning that if you reverse them, you can always reverse a sequence, except that it's going to start acquiring fractions, so those numbers are no longer going to be integers. But you can formulate the same problem. You are interested in whether something is 0 or not. It doesn't matter whether it was a fraction which has a numerator equal to 0, or if it's an integer. So let's call a bilinearly recurrent sequence. We start with this one over Q, so we also go with it into the past. And the question is there a 0 anywhere in the future or in the past? And we call a linearly recurrent sequence to be simple if its characteristic roots are simple. I didn't want to tell you much about that, but basically what happens with those guys is that to this recurrence, you can associate something which is a polynomial. That polynomial has some roots. And if those roots are simple as roots, so they are not roots of the derivative, then this sequence is called simple. So for the Fibonacci sequence, the equation is x squared minus x minus 1, which has the two roots, 1 plus root 5 over 2 and 1 minus root 5 over 2. These ones are called the golden section, and it's reciprocal. And they appear in very beautiful sort of patterns and architecture and so on. And the vast majority of the linearly recurrent sequence are simple. What do I mean the vast majority is that suppose that you select some random polynomial and then you try to factor it out and you see what its roots are. It turns out that the roots of a random polynomial are simple. In order to create non-simple roots, you really have to work hard in order to get a polynomial that doesn't have simple roots. And let's go to the state of the art. What's known about that? So for linearly recurrent sequences, which are of order at most 4, the Skolem problem is decidable. And this has something to do a little bit with like big roots, the roots of large absolute value. If it has just one root that's bigger than the other ones in absolute value, that's called a dominant root. And for this, the problem is very easy. It's basically high school mathematics. If you go to two complex conjugated roots, which are big and everything else is small, here you need some ingredient, which is due to the work of Alan Baker, which was a British mathematician. He passed on a few years back, and it's called lower bounds for linear forms in logarithms of algebraic numbers, some terrible terminology. And it earned Alan Baker the Fields Medal in 1970. So there is a lot of very deep mathematics that goes into this particular theorem where you have, let's say, two roots which are dominant. And then there's a little geometrical trick that if you have 3 dominant roots, kind of the same thing goes on. And then already if you have 4 dominant roots, things change and you can't do it anymore. So for a bilinear recurrent sequence of order at most 4, the Skolem problem is decidable. We prove that for z-reversible linear recurrent sequences of order at most 7, the Skolem problem is decidable. But you see, it looks like we really did a huge progress from the number 4 to the number 7. But what's built in there, it's called something z-reversible. So what z-reversible implicitly means, it means that if you look at that characteristic polynomial, the last coefficient is plus minus 1, because the last coefficient, that's the one you have to divide by in order to be able to go into the past. So you're basically looking at, let's say, polynomials of order at most 7 with the property that their roots are algebraic units. And those ones can't really be, let's say, 4 of them that have the same absolute value or something like that. So while this one looks like impressive, it's actually an exercise in Galois theory. You can give it to the students in the honors algebra once they learned about Galois theory. So there is a class of sequences that it's referred to MSTV from the name of these guys, Mignot, Shori, Tiedemann, and Vereshchagin. So the MSTV property, it's a particular property of linear recurrent sequences of order at most 4. And the ones that are of order 5, here is the first bad example. Consider this recurrence. If you want to kind of draw the roots around, it has 4 roots that have the same absolute value, which is the square root of 65. And it has a root that's a little bit smaller, and you can give some random initial values. And this, for this particular one, there is no sort of theorem that says that, well, the theorem says it has finitely many zeros, but nobody knows how to compute them given any random initial terms. So in general, are hard examples of order 5. They all kind of have the same structure. They have 4 complex conjugated roots, which are all equal in absolute value. And somehow any 2 of them are not really co-prime. There is some prime sitting inside there, and that kind of messes it up. So many problems in mathematics and computer science are solvable subject to very standard conjectures. So here is I'm going to put out some conjectures there. For example, Miller's polynomial time test for primality. The correctness relies on the Riemann hypothesis, the security of the RSA, and pretty much all of modern electronic commerce is based on the folklore conjecture that factoring is not in polynomial time. This is what it's believed. Nobody could find a polynomial time algorithm to factor integers. And decidability of the first order theory in real arithmetic with exponentiation. This one is subject to something called Schanuel's conjecture. And I'm going to talk about Schanuel's conjecture now in the next slide. What Shanuel conjecture says, it says, it basically comes from the fact that the number denoted little e in mathematics, which is the natural log, which is the base of the natural logarithm, it's a transcendental number. And then it turns out that if you take algebraic numbers, let's say, of course, if you take 2 and if you take the square of e, that's also transcendental. It doesn't obey any polynomial equation, but you can also take e to algebraic numbers, e to the square root of 2 or things like this. They are also transcendental. So this Shanuel conjecture tries to somehow quantify if I take the exponential function with more than one number. So suppose that I have n complex numbers, and I take the exponential of those n complex numbers. And then I put all this together with q. So I ask, what is the transcendence degree? The transcendence degree, it's, let's say, inside this field, what is the maximal number of numbers that you can find in such a way that there is no polynomial with rational coefficients that kills this set of numbers? So for example, one of the things you could do is to take alpha 1, alpha 2, alpha n to be natural logarithms of algebraic numbers. Because once you take them to be natural logarithms of algebraic numbers and you take the exponential function of that, those guys, the exponentials of those guys become algebraic numbers, so they don't contribute to the transcendence degree. And therefore, this kind of statement would tell you something about the transcendence of logarithms. So is there a polynomial, for example, of 2 variables that vanishes in the pair natural log of 2, natural log of 3, for example? We don't know about that. We know that those things are linearly independent over Q, but not algebraically independent. So equivalently, it's you have n complex numbers which are linearly independent over Q. If you wonder what does linearly independent over Q means, for example, if one of them is the sum of 2 others, let's say I take x, y, and x plus y, then when I look at e to the x plus y, that's the product of e to the x and e to the y. So you want to avoid things like this, where you obviously have some sort of an algebraic relations between things. So you take these complex numbers, you assume them to be linearly independent over Q, and then this would say that within this set, one can find at least n numbers that are algebraically independent over Q. And I said that the relevant case is when the alpha i's are logarithms of algebraic numbers, because then the e to the alpha i's are algebraic numbers themselves, they disappear. And then if the conjecture is true, this means that these logarithms of linearly independent algebraic numbers over Q are actually algebraically independent. So here are some things about algebraic and transcendental numbers. We know that E is transcendental, pi is transcendental. What about E plus pi or E times pi? Well, not both of them can be algebraic, because if they are both algebraic, then E and pi are algebraic. So in particular, E plus pi and E pi cannot be both rational. What about this guy, for example, that kind of a polynomial? So what is actually believed is believed that E and pi are algebraically independent. And this is a consequence of the Shanuel conjecture, because you can take alpha 1, the first complex number to be 1, the second complex number to be I pi, and then e to the 1 is e, and e to the I pi, there is this beautiful formula that says that e to the I pi is equal to the number -1, but -1 is an algebraic number. So somehow this set of 4 guys should contain 2 algebraically independent numbers. And certainly they can't be 1 or -1. So they should be e times pi and e. And I is an algebraic number, is the square root of -1. So its 4th power is equal to 1. So you can remove that. And then you get the statement that e and pi are algebraically independent, assuming the Shanuel conjecture. So in particular, any non-zero polynomial with rational or algebraic coefficients, p of e pi cannot be equal to the number 0. Of course, you can write tautology like e plus pi everything square equally square plus 2e pi plus pi square, but that's not really a serious business, because that, if you put everything in the left-hand side, you get the 0 polynomial. Okay, so let's go back to our sequence. We take this linear recurrent sequence and then we go into the past with it. So if AK is invertible modulo some modulus, so if I go into the past, I basically have to divide by the last coefficient. So if the last coefficient is co-prime to some number m, then the entire bi-infinite sequence is well defined as far as the modulus m is concerned. So I'm going to ask that m and a sub k are co-prime. For example, for this sequence, u sub n plus 1 equal twice un, I can't really take it mod 2, because you see 2 is equal to 0, and we were told in school that you cannot divide by 0. So you should not divide by, you should not take the modulus to be 2. But you can take the modulus to be 3. If you take the modulus to be 3, then what does 3 think about 1 half? Well, who is 1 half? 1 half is something with the property that if I multiply it by 2, it becomes 1. But then modulo 3 says, aha, who is something that I multiply it by 2 and it becomes 1? It's 2 itself, because 2 times 2 is 4, and modulo 3 that is equal to 1. So 1 half is the same as 2. And then 1/4 is the same as the square of 2. The square of 2, because it's the square of 1 half, and the square of 2 is 1 modulo 3, and so on. And you can do it mod 5 and so on. So here is a conjecture that comes from Skolem himself. Skolem conjectures the following thing. Suppose that you have a bi-infinite linearly recurrent sequence over the rationals, and suppose that it has no zeros, then there is a witness. What does it mean, a witness? There is a positive integer m that is co-prime to that last coefficient a sub k, such that this sequence has no zero modulo m. And the word simple is important there, because, for example, you can take this sequence, 2 to the power n times 2n plus 1, and this sequence doesn't have zeros, but modulo, I mean, it has a 0 if you want to stretch it to say n equal negative 1/2, but that's not an integer. But it has zeros modulo every number m, because I take modulo every number m, that m has some power of 2 in it, and some odd part of it. So I can make 2n plus 1 to be a multiple of the odd part of m, and that's how I kill the odd part of n. And I can take n to be large enough to beat the power of 2 that sits inside m, and then somehow that there is some 0 of this sequence modulo m for every m. But if the sequence has simple roots, then it is conjectured by Skolem that this conjecture is true. So look at this paper. It's almost 100 years old, 1937. So the bi-infinite, I already gave you the example, because it could be that 0 is somewhere in the past. I'm just showing you a segment of it going towards infinity, where I already avoided the zeros, which are finitely many anyway. So here is what it says, the mathematical statement. You take a recurrence, that recurrence un plus k equal a1 un plus k minus 1 and down to ak un, where all the coefficients and initial terms are integers. And then suppose that the bilinear recurrent sequence is simple. So that, to decide that it's simple, then you will have to take some polynomial, and you will have to maybe compute the GCD of that polynomial with its derivative and so on, and decide that they are co-prime if you don't want to factor it. So that will be the easy way to do it. And then this sequence has no zeros if and only if, for some positive integer which is co-prime to the last coefficient of the recurrence, un is not equal to 0 modulo m. And of course, one implication in mathematics, when you say if and only if, say this is true if and only if this is true, then you have to argue in two ways. You say, suppose that the first one is true, and I have to find some argument that proves that the second one is true. And then you say, suppose that the second one is true, and you have to find some argument that proves that the first one is true. Well, one of the things is easy. If there is such a modulus, then of course there can be no zero, because if there is a zero, then that zero will remain a zero modulo every modulus, including that particular m. So if there is a modulus m for which and this is an easy decision problem, because the sequence modulo m is periodic. So if you compute it large enough, it's going to loop. And then you say, oh, from now on, no new patterns can appear. And if inside that pattern there no zero has appeared, it means that it will never appear. So that's one way to decide it. So equivalently, a simple bi-infinite linear recurrent sequence over the rational has no zeros, then it's witnessed modulo some integer. And then we had a little contribution a few years back where we proved that the order 5 is decidable if we assume the Skolem conjecture. And then maybe one of our best works until maybe this year is an algorithm that takes an input, a simple non-degenerate linear recurrent sequence, and produces its finite set of zeros. So if you give us a simple linearly recurrent sequence, then we can find all the zeros. However, the termination is guaranteed assuming the Skolem conjecture and something called the Piadic-Schanuel conjecture, which is something even worse than what I told you that the Schanuel conjecture is, and I'm not going to go into those details. But the point is that those two conjectures are only needed to prove termination, not correctedness. Meaning that if our algorithm finishes and it gives you some printout and it says, look, this is a certificate that these ones are the only zeros and there are no other ones, then this certificate is not subject to any conjectures. That certificate is fine. However, mathematically, we cannot prove that this program terminates unless we are assuming those conjectures. And this program exists. It's called the Skolem tool. If you go to the Skolem tool, basically, you're going to see a window like that. It's going to ask you for A1, AK, and U0, UK minus 1, which come from the recurrence. And it's going to ask you to swear solemnly that your sequence is simple, because this program is not going to go and look at the polynomial and try to find out if it's simple or not. It's going to go and it's going to do whatever it's trying to do. So here is, for example, an example. You take k equal 1, 2, 3, 4, 5, 6, 7, 8. You take those AIs, which are 6 minus 25 and so on, and the UIs are 0, 0 minus 48 and so on. You already see 3 zeros there in the first, second, and fifth position. We labeled them the 0, 1, and fourth position. So it's outputting something. It's outputting 0, 1, 4. So, and then it's outputting a very long list of things. So what that very long list of things is, it's a set of witnesses. It's outputting a finite set of witnesses with the property that if n is any positive integer, which is not one of the numbers 0, 1, and 4, then there is some modulus in that list of witnesses, which witnesses that u of that value of n is not equal to 0 modulo of that modulus. So in that sense, what I'm saying is that the certificate, you don't need any conjecture to check that that certificate is true. You only need the conjecture to say that mathematically this program will terminate. That's what you need the conjecture for. But other than that, the algorithm knows exactly what it has to do. It has to assume that something is non-zero, and that's given by the conjecture. But then when you actually run it, that number that you're assuming that is non-zero, it's usually 0.1 or something. It's not like you have to compute a million decimal digits to say, aha, it's not equal to 0. It's not equal to 0 because of quite obvious reasons. Alrighty. So now let's go a little bit and talk about, I showed some algebraic number theory that contributes there. Let me show you some analytic number theory that contributes into the problem. So let's talk about large zeros of linear recurrent sequence. So suppose that you have a linear recurrent sequence. It's given by these 2k values. And then in mathematics, you want to quantify something and you want to say how complicated something is. So you assign something to it, which is called a height function. For example, for algebraic numbers, the height is an important element because the height of an algebraic number is a root of a polynomial with integer coefficients. And somehow, the larger the degree of that polynomial is and the larger the coefficients are, the feeling is that the more complicated this algebraic number is. So then you have to quantify that in some way by saying, oh, maybe the height is the maximum between the degree and the absolute value of all the coefficients. And there is something like this. It's called the naive height. There is something else that's called the vial height, which is much more complicated, but they are somehow equivalent. So let's define the height of this linear recurrent sequence to be the maximum between the length, all the coefficients, and the initial terms, and some number 12 there because we were going from one inequality to the next, and that's why we needed the number 12. So you can say, how big is the zero of a linear recurrent sequence with respect to this height? For example, we don't know of an instance of a linear recurrent sequence which has a zero that's as big as the exponential of the height. I'm not saying that this doesn't exist. I'm saying that we don't know of such an example. We know an example, for example, there's something called the Bechtel sequence, which is a sequence of order 3. It starts with some benign values 0, 2, and so on. And it has a linear recurrence relation that has coefficients 1, 2, and plus minus 4, or something like this, and it has a zero in position 52. So this is already big compared to those small numbers. However, 52 is not the exponential of 4. The exponential of 4 is much bigger than 52. Already square is 7 point something. So, okay. So, of course, that doesn't mean that such linear recurrent sequences, they don't exist. But here is our theorem, our conjecture. The conjecture is that if un is equal to 0, then n is smaller than twice the exponential sixfold times of this h of u. And this is very good to write a paper like that, because once you write a paper like that, then somebody's going to quote it and say, I reduced the exponential 6 to exponential 5 of hu cubed or something like that. So, oh, that's great. So anyway, in the rest of maybe 10, 15 minutes, I'll try to give you a brief history of the primes and to tell you why we believe this conjecture to be true. So Euclid, about 300 years ago, he proved that there are infinitely many prime numbers. And this is still the proof that we use when you teach the very first course in number theory, and you prove there are infinitely many primes. You see Euclid's proof. He assumes that there are finite many primes. You multiply them, you add 1, you get an integer that's bigger than any of them and not a multiple of any of them. So it must contain a prime. Now Gauss, in 1782, in a letter to Encke, he said, as a boy, I considered the problem of how many primes are there up to a given point. And from my calculations, I determined that the density of the primes around x is 1 over log x. So here is what Gauss says. Gauss says, take a number x, take a segment of length L there, and count the number of primes that are inside that segment, L. And according to Gauss, the number of primes in the blue segment is L divided by log x. That's a good exercise. For example, if you take an interval of length 1,000 around 10 to the 6, and you say, how many primes would I suspect to be there? Well, it's 1,000 divided by the log of 10 to the 6. The log of 10 to the 6 is 6 log 10. Log 10 is 2 point something. So it's maybe 1,000 divided by, let's say, 15. So then you get some guess there. Maybe there are 60, 70 primes or something like that in that interval. So how many primes are there from 0 up to x? This is something denoted by pi of x. If the density should be 1 over log x, then the total number of them, you integrate that density. It's the integral from 0 to x of 1 over log t. You shouldn't be scared to integrate it in 0. It looks like a discontinuity, like singularity there, but it's not. And this is denoted Li of x, and that's asymptotically equal to x over log of x. And this actually became a theorem, but it became a theorem only about 100 years after Gauss, because Gauss was doing his experiments in 1792, or what was it, 1792, yes? And the prime number theorem became available in 1896, and it was proved by these two French mathematicians, Hadamard and Delavallee-Poussin. They proved that indeed pi of x divided by that logarithmic integral, you take this ratio, and this ratio tends to 1 as x tends to infinity. But the prime number theorem doesn't say anything about the difference. Okay, fine. So pi of x and Li of x are kind of the same size, which means that if I subtract them, I get something that's smaller than the common size of them. But how much is it smaller? And this is where the Riemann hypothesis comes in. Now, one can talk a whole hour just about the Riemann hypothesis and the way it is formulated. It's formulated in a very convoluted and strange about way, because you have to sum up the reciprocals of all the positive integers. You have to raise them to some exponent. That exponent is a complex number. You already start scratching your head. What does it mean, 2 to the power 1 plus 10i? So then you have to define what is that modulus and so on. Then you have to get some analytic continuation. You have to drag it towards the real part of s bigger than 0 and so on. However, this is what's important. Von Koch proved in 1901 that assuming the Riemann hypothesis, the difference between pi of x and Li of x, it's at most a constant times square root of x log x. That's what the Riemann hypothesis says. And you can take that. So if you're ever in trouble and somebody says, exactly is the Riemann hypothesis, That's what the Riemann hypothesis is. So learn that because it could save your life someday. You see, this guy probably, if he knew the answer, probably he got away with it. So anyway, you can put some constant there inside the O. You can put 1 over 8 pi. So Schoenfeld proved that, assuming that the Riemann hypothesis is true, that for x, at least that value, then the difference between pi of x and Lie of x is at most root x log x divided by 8 pi. Of course, there is life without the Riemann hypothesis. Even without the Riemann hypothesis, there are estimates, but those estimates are not so good. So don't be fooled by x over log x to 3/4 because that's not the main term. The main term is the exponential of minus square root of log of x. That is a very strange function. When I was a high school boy, I didn't think that those functions exist because what they teach you, oh, the logarithm is something that goes to infinity kind of slowly. And then the powers also, the roots also go to infinity slowly, let's say the square root and the cube root. And any root is bigger than any power of the log. But somehow, what's in between? Well, this is what is in between. Because the root is the exponential of a constant times the logarithm, and the logarithm is the exponential of the double logarithm. So whatever you put between the double logarithm and the logarithm inside the exponential, in particular the square root, then that's going to be something that lives between these two worlds, and it interpolates them. Okay, so let's look at gaps between primes. Let's define g of x to be the maximal gap between primes. So of course, the twin prime conjecture asserts that the infinity often p and p plus 2 are prime. So p and p, so the gap between primes should be 2 infinitely often. But here we are calculating the maximum of the gap, not the minimum. And then there's a theorem by Baker, Harman, and Pintz. I think it's still the state of the art, which says that this gap is at most x to the 0.525. And Cramér, assuming the Riemann hypothesis, he proved that this maximum gap is at most a constant root x log x. Now, on the other hand, it's not log of x. If primes would be uniformly distributed, it should be log of x. But these very smart people, you see in that list, there's 2 Fields medalists in that list, Maynard and Tao. And they prove that infinitely often the gap between consecutive primes is slightly bigger than the logarithm of x. It's the logarithm of x times something else that tends to infinity, which is the double log multiplied by the quadruple log divided by triple log. So that you would read it like log divided by log. And there's a joke in the community saying, what are the last words of a drowning analytic number theory? Log. So the point is that, of course, the more iterated logarithms you have, the slower you go to infinity. So the one that goes to infinity fastest after the log is the log sub 2, because the other ones go slower. So what multiplies the log in that expression is something that goes to infinity very slowly. Okay, Cramér, he has this philosophy, which is actually used quite often. Says in investigations concerning the asymptotic properties of arithmetic functions, it's often possible to make an interesting heuristic use of probabilistic arguments. So here is what game he was playing. He takes a bag of black balls and white balls, and he says, let's suppose that the black balls are the primes and the white balls are the composites, and we start extracting balls from there, and the probability of at step n of extracting a black ball is 1 over the logarithm of n. And he takes all the sequences that have this property. And he says, well, because of the prime number theorem, somehow the primes is one of the sequences that has this property. And he proves that as you go along all the sequences that has this property, then with probability 1, the lim sup of the gap divided by the square of the logarithm is equal to 1. So for almost all sequences that arise in that way. And then he says, well, but you see the primes are a sequence that's like that. And because of that, maybe this is also true for the primes themselves. So the difference between Pn plus 1 and Pn is at most logarithm of n squared. Well, it turns out that this was false. It was proved by Helmut Meyer that there are some restrictions there. And the restrictions come from the fact that, for example, in the ball scenario, there is no obstruction of extracting, let's say, 2 prime balls consecutively. But in the world of the prime numbers, you cannot have consecutive primes. You have 2 and 3, but after you have passed 2, all the primes are odd. So once I have extracted a prime, then I know for sure that the next one is not prime. Maybe the one after it is prime, but that I don't. So because of that, there is some tweaking there. But some people believe that if you tweak that, number 1, to something a little bit bigger than 1, then in fact, this conjecture should be true. That is that the gap between primes should actually be at most a constant times the square of the logarithm. And the largest observed value for this constant, because you can do numerical experiments. You can take p sub n plus 1 minus p sub n divided by log square of p sub n, and you can plot those numbers up to n equal 10 to the 12, 13, 14, whatever the list of primes is known. And the largest observed value is that one. Now, there is something that we call bad primes for our Skolem problem. So it looks like somehow I went to prime numbers and I forgot about the linearly recurrent sequences. Well, let's go back to linearly recurrent sequences. And let's say that a prime is bad if it's a large prime number that divides a large term of a low height linearly recurrent sequence. So I take a large integer x. I consider a linearly recurrent sequence of small height, where the height is the 6-fold iterated logarithm. You saw these iterated logarithms are quite popular, even from the world of Maynard and Tau and so on. So it's a sequence that starts very low, and this prime is very high. So this is the low sequence, it's there. And then the prime is called bad if it has the property there is some index up to at most x to the 1/4, although x to the 1/4 you can even replace it for our purposes with the logarithm of x squared or something, such that p divides the mth term, and the mth term of that sequence is not equal to 0. And you say, okay, what is the big deal with that? So we prove that. So the definition of bad prime is somewhat more involved, but you can kind of see what it is in here. And then what we proved that the bad primes are very scarce. In fact, they have null density within the set of all primes. We don't even know if a single bad prime exists, because in order to find a single bad prime, you have to find a prime that divides some term of a very low sequence. But since very low sequence is the 6-fold iterated of the logarithm, then you see that prime should be huge. And we don't even know primes in that range. We can't test if they are primes. So good primes are prime numbers that are not bad. So our theorem says that most primes are good. In fact, the bad primes have a very small counting function, like x to 2/3 or something. Okay, so since the good primes are basically all the primes except some bad ones, which are very few, we can suppose that the Cramér conjecture holds for them as well. I mean, Cramér formulated his conjecture just based on purely probabilistic argument. So why wouldn't our good primes also do that? So suppose that the strengthened Cramér conjecture holds, and here's our theorem. If the strengthened Cramér conjecture holds, then there are no large zeros. So in particular, this solves completely the Skolem problem, saying the largest n such that un is 0 is at most twice the exponential 6-fold of that number h of u, which is the max between the coefficients and the initial terms and so on, but it's subject to the strengthened Cramér conjecture. And the proof is kind of funny, because what it is, suppose that you have a 0 at a very large position, and then you start and you shift it around. You say, let's suppose that this n, I'm writing it under the form m plus some other number, where m circulates between 1, 2, 3, and so on. So because of the Cramér conjecture, by the time m goes to the square of the logarithm or something, I will find a representation like this of the form n equal that number plus a prime. But then if I go even further, I go to power log of n cubed or something like that. Then I find at least log of n representations of that form. So when I look at u sub n is equal to 0 and I reduce it modulo those kind of primes, I apply something called the Fermat's little theorem and so on, and a lot of things goes away. And it ends up being p is a divisor of this value of u sub m, of this sequence at a very low level, which makes somehow p a bad prime. But we said we don't talk about the bad primes. We only talk about good primes. But there are lots of ingredients that go in that. You have to count explicitly the upper bound on the total numbers of zeros and so on. And this paper, actually, when we wrote that paper, we didn't even know about the result of Amoroso and Viada, about the double exponential. We were using Schmidt's thing with a triple exponential. And that's why we get a sixth-fold exponential. So we can probably get a fifth-fold exponential for free, just going in there and replacing some of the thing. So of course, this is just basically the start, and then it can go from there. Alrighty. So that's the high-level key idea, to leverage the strengthened Cramér conjecture to infer bounds on the magnitude of zeros, because we have bounds on the number of zeros, but somehow we have to transform them into bounds on the magnitude of zeros. And that's where these results about primes come into the picture. Thank you.
Very much for the great talk. Do we have questions for our speaker? Don't be shy. Here comes the question.
Hi, thank you, Florian. So it seems interesting. You have an algorithm that works if things are true, but then
Yes.
this last bit is totally different. And I guess, I mean, in practice, an algorithm that corresponded to this is just searching through all of them, which would take.
Yes, that would be the most trivial possible algorithm. I
So
mean,
is there a chance of a feasible algorithm that goes with this? Could the bound be sort of low enough that there would be a feasible way to search?
I don't really know. I was trying to think about that, but I was even trying to construct, let's say, bad primes, but it's not so easy to construct bad primes, exactly because we don't know of linearly recurrent sequences that have large zeros. I mean, most sequences, they don't have any zero at all, right? So then it looks like these funny sequences, like the Berstel sequence. Somebody cooked them up there in some way, because they shouldn't really be there. So I don't know how to, basically, I don't know how to answer to your question, just because I don't think we will find examples to work with.
Any other questions? Do we have questions from our online participants? Not at the moment. Here we go.
My question to you will be, why Skolem? Why didn't you go to 3x1 problem? Why this one specifically?
Oh, just because so many people worked on it, and it kind of became a measuring stick in the community. So now, because so many people worked on it, and with limited success, now we believe that it is a hard problem. So now suppose that somebody gives you another problem which you can't solve. If you can solve it, that's great. But then if you can't solve it, you at least should give a reason why you can't solve it. You can't say that you can't solve it because you have no idea how to do it. You have to blame the problem. You have to say the problem is hard. It's not us who are incompetent. So then, if you take this problem and there is some way in which you can reduce it to the Skolem problem, then you say, aha, my problem is at least as hard as the Skolem problem. Therefore, it's a legitimate hard problem. So it's more like a measuring stick by now. So.
Yeah, I understand. And in our maths lectures, especially in actuary, most of them will be like, I don't like the Skolem one because it doesn't have any finance. I don't get it.
I see. Well, I'm sure you can get some big prizes if you solve it. So there will be some finances there.
There is just a medal.
It depends who gives it.
There's one more question, please.
If I can ask a second one, I was just thinking if the Skolem conjecture is true, is there any heuristic sense of how big the modulus might be that witnesses?
I see. Yeah, we did think about that, but you see, it is built in our algorithm, the Skolem conjecture. Because you see, the Skolem conjecture, it's basically just the negative of the existence of a zero. So if there is no zero, then you find this witness, okay? But then, now let's suppose that there is a zero. then what do you do? And this is what we do, basically. What we do, we take the 0 and we translate, we put it inside the origin. And then we prove that there is some sort of a modulus with the property that if you split all the integers starting from 0 modulo that modulus, then on the branch, which is multiples of that modulus, the only 0 that's there is the 0 that's in the origin, and there's no other 0 at all on that ray. So now that I have that ray, I throw away that ray, and then I can go on the other ones, which are integers, which are 1 modulo that modulus, or 2, and so on. So now you see, I started with a Skolem problem with 1 sequence. I found a 0, but now I have m different sequences. For each one of these, I have to go to the Skolem conjecture. If there is no 0, then Skolem conjecture is going to tell me. And if there's a 0, then again I translate it and then I branch it like that. So the more zeros you have, the more complicated it becomes. But there is a bound on the number of zeros, so the algorithm does terminate. But so in practice, those moduluses are quite small, but we don't have, let's say, a bound, a theoretical bound for them.
Okay, I think there are no more questions. Then, Florian, thank you very much for your talk. And there's a little